Okay, so we're continuing our discussion of heat. And when we left off, we were talking about what internal energy is. So we were actually, if I flip back here, looking at this slide here where we had 3 pots of boiling water. They're all the same temperature, so the temperature is the same. But since the internal energy is the total amount of energy of all the molecules, if we have 3 pots of boiling water, that means that we've got 3 times the amount of um, internal energy. So if we think of internal energy as being the sum of all of the kinetic energy of all of the molecules, we can quantify the internal energy by basically summing up all of those kinetic energies of all those little molecules. And so this formula gives us the internal energy. That's the total internal energy U. We're going to use U to represent internal energy. Is 3/2 nRT, where N is the number of moles, R is a constant, and T is the temperature. So this is for the internal energy of a monatomic gas. So here we have our monatomic atom bouncing around the slide there. So what's the difference between monatomic and diatomic? Well, some molecules like oxygen, for example, tend to have 2 atoms together, O2. So we've got 1 oxygen here and another oxygen here, and they're linked together. Now, if we look at the kinetic energy of a molecule like this that's made up of 2 atoms, it is both going to translate or move, and it's also going to rotate. So we have 2 types of motion there. Whereas if we're talking about one single molecule here, it doesn't really rotate. It just essentially moves back and forth. It just translates. And so that's why we're able to quantify the kinetic energy in a nice simple formula for a monatomic atom or particle, because it's only has one type of motion. It's just translating. It's not rotating. Okay, so now we're going to introduce this concept of specific heat. And so what specific heat is, it's the amount of heat energy required to change the temperature of a material by a certain amount. So in other words, some materials will heat up more easily than others. So if we look at the chart here that has specific heat of various things, aluminum, actually, no, let's look here at copper. Copper has a very low specific heat, 390. That's pretty low compared to some of these other things. Well, it looks like maybe mercury and silver are also pretty low. So what does that mean in terms of how these materials might be used, or what characteristics they have? If you have a cooking pan, for instance, it might be made of copper, or at least be copper lined. Why is that? Because it doesn't take as much energy to heat up the temperature of copper, because it has a relatively low specific heat. Same thing with mercury, although mercury is liquid at room temperature, so we can't make a pan out of mercury. But we have silver. Now, silver is sort of a precious metal, so it doesn't get used a lot for common household or industrial items. But if we wanted to, we could use silver to make cooking pans with. It would also heat up even more quickly than copper. So these things, they heat up. So things that we want to heat up quickly with a minimal amount of energy being put into them, we would want to use something with a low specific heat. On the other hand, if we look here, alcohol, ethyl alcohol has a very high specific heat. Even higher yet, the highest I think on this chart it looks like, is liquid water. Water takes a lot of energy to heat up. It's has a very high specific heat. And so we can quantify specific heat here by, or at least use specific heat to quantify the amount of heat flow. Q is used to represent flow of either fluids or, in this case, heat energy flowing from one object to the other. So the amount of heat that needs to flow into a material in order to raise its temperature is equal to its mass. So the more stuff you have, the more water you have, the more energy it's going to take to heat it up. Its C, its specific heat, which can be found here on this chart, and then delta T, how much do we want to heat it up by? So the more we want to heat it up, the more heat it's going to require. The more of it we have, the more heat it's going to require. And the more or the higher its specific heat is, the more energy it's going to require. So gases can also have a specific heat, but when we're talking about the amount of heat energy necessary to raise the temperature of gas, we need to make sure that we're keeping that gas at a constant pressure and a constant volume. If we allow the pressure or volume to fluctuate, the calculation gets much more complicated. And so if we're going to deal with any problems involving the amount of heat energy required to raise the temperature of a gas, we need to make sure that we specify constant pressure and constant volume. Let's look at an example here where we have a cast iron pot. We want to know how much heat is needed to raise the temperature of it while it's empty, and it has a mass of 20 kilograms. And we want to raise its temperature from 10 degrees Celsius to 90 degrees Celsius. So 90 minus 10 is 80. 80 degrees Celsius, that's the delta T that we want to raise this temperature by. The mass is 20 kilograms. And the C, the specific heat of iron, if we flip back here to this table here, it's 450 joules per kilogram degrees Celsius, or 0.11 kilocalories per kilogram degrees Celsius. So let's just go ahead and do it in joules, how many joules of energy it will take, and that's going to be 450. 450 joules, let's double check the units there, joules per kilogram degrees Celsius. Joules per kilogram degrees Celsius. Okay, and then in part B of the question, we want to know how much energy would it require if the pot was filled with 20 kilograms of water. So let's first look at the cast iron here. We've got these variables, and so the heat, Q, the heat that needs to flow into this pot for just the pot when it's empty, is mc delta T. So the mass was 20 kilograms. Oops, there we go. The specific heat, we had looked that up. The specific heat is 450 joules per kilogram degrees Celsius. So the degrees Celsius is actually on the bottom of the fraction bar here. I had put it, I wasn't very clear on that here on this slide, so let's make sure I indicate that it is in the denominator of that fraction or ratio. And the delta T we want to change it by is 80 degrees Celsius. So 20 times 450 times 80 gives us 720 kilojoules. Oh, my pen tool kind of malfunctioned there. Erase that. All right, let's get back to the pen. What are my units here? Oh, yeah, kilojoules. Kilojoules. Okay, so is that a lot of energy or not a lot of energy? Well, let's compare that to the heat that's going to be required to heat up the water. The mass of water is given in the problem statement, I believe. What if it's filled with 20 kilograms of water? So we're doing sort of an apples to apples comparison here. We've got the same mass of water, so that's 20 kilograms. But what's going to be different here is C, the specific heat. If you'll recall from that chart, water was one of the highest values. It was 4,186. So 4,186 joules per kilogram degrees Celsius. And we're changing it by the same temperature, 80 degrees. And so that is 6,700 kilojoules. So you can see that's a huge difference. 720 kilojoules to heat up the cast iron pot is nothing compared to the amount of heat required to raise the temperature of the water inside it. So that's one reason why we use a material like cast iron to make pots like this, because it doesn't require as much heat to warm it up, especially when we compare it to the food, which is probably mostly water, that we are cooking inside of it. That takes, by comparison, a lot more heat. Okay, so this device you're seeing here is called a calorimeter. So essentially it consists of a cup filled with water, has a thermometer, has a stirrer to make sure that the heat energy is evenly dispersed in the water. And then we want to try to isolate this system, to close it off from heat that might be in the surrounding room. So it is insulated. We have this insulating jacket, and we have air, this airspace in between. Air is an excellent insulator. So we have this insulated cup of water, and what we're trying to do is keep it, keep the outside energy out, so that we can study the heat in the cup itself. And so I'll introduce this problem here, but as I look down at my timer, I don't think I'll have time to finish the problem. We'll have to do that in the next video. But you can use a calorimeter like this engineer is in this problem. He wants to determine the specific heat of a new metal alloy. And so he has a sample that is 0.150 kilograms, that's the mass, and he's going to heat it up to a temperature of 540 degrees Celsius. He will then put it into the calorimeter. The calorimeter has 0.400 kilograms of water inside it, and it is currently at a chilly 10 degrees Celsius. And so, and also the cup is made of aluminum, and it has a mass of 0.200 kilograms. What's going to happen is the metal alloy is going to go into the cup, and it's going to raise the temperature of the water and the cup. So the heat is going to flow out of the metal into the surrounding system until everything comes to equilibrium. The final temperature is going to be 30.5 degrees Celsius, at which point we will be able to determine what the specific heat of that alloy was. So we'll do that in the next video.